Good day. For those of you who do not know us, we're the instructional staff for EC 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to have a binary and hexadecimal number tutorial. In this tutorial, we will review binary numbers, convert binary numbers to decimal, convert decimal numbers to binary, add two binary numbers, convert a binary number to hexadecimal, convert a hexadecimal number to binary, and there will be two bonus sections that you can skip, but they include converting a decimal number to hexadecimal and multiplying two binary numbers. It should be easy enough for you to remember at least the first few binary numbers. For example, powers of 2 are just 1 with 0 or more zeros after it. So 2 to the 0 is just 1. 2 to the 1 is a 1 with 1 0 after it, or 2. 2 to the 2 is 1 with 2 zeros after it, and 2 to the 3 is a 1 with 3 zeros after it. So 1 0 0 0 is 8. If we add 1 to the last three of those numbers, well, 2 plus 1 is 3, 4 plus 1 is 5, and 8 plus 1 is 9. Similarly, if we take the last two numbers, notice that 4 plus 2 is 6, 8 plus 2 is 10. Similarly, 4 plus 3, remember 1 is 3, so 4 plus 3 is 7, and 8 plus 3 is 11. Now, if all of the bits are 1, it means it represents a number of the form 2 to the n minus 1. So just a single 1 is 2 minus 1. 2 ones is 2 to the 2 minus 1, or 4 minus 1. 3 ones is 2 to the 3 minus 1, which is 8 minus 1, or 7. And 4 ones is 2 to the 4 minus 1, which is 16 minus 1, or 15. Now, here we have a few slightly larger binary numbers, but also on the right-hand side, I have their corresponding hexadecimal digit. So 1010 is again 10, but that's also the hexadecimal number A. If I add 2 to 10, I get 12, which is the hexadecimal number C, and if I add 2 to 12, I get 14, which is the hexadecimal number E. Now, I always screwed this up because A, C, and E are the first, third, and fifth letters of the alphabet, but A, C, and E are actually even hexadecimal numbers. So just to remind myself, I have in the back of my head this short little phrase, ace is even. So A, C, and E are even, B, D, and F are actually odd hexadecimal numbers. So if we add 1 to each of these numbers, we get the other remaining 4-digit binary numbers. So 1011 is 11, 1101 is 13, or D, and all ones is 16 minus 1, or 15, which is also represented by the hexadecimal digit F. Now, recall from secondary school that 5083 means 5 times 10 to the 3, or 5,000, plus 0 times 10 to the 2, or 0 hundreds, plus 8 times 10 to the 1, or 80, plus 3 times 10 to the 0, or 3. In general, if I have a 6-digit decimal number, then this just represents the sum of the digits times 10 to the appropriate power. In this case, D5 times 10 to the 5 plus so on and so forth until the least significant digit is multiplied by 10 to the 0, or 1. The same is true in binary, except rather than powers of 10, we have powers of 2. So 1011 means 1 times 2 to the 3 plus 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0, which is just equal to 8 plus 2 plus 1, which is 11. In general, the binary number here, an 8-digit or bit binary number, just represents the most significant bit, B7, times 2 to the 7, plus successive bits multiplied by appropriate powers of 2, all the way down to the least significant bit, B0, times 2 to the 0, which is just 0 or 1. Now, the difference between binary and decimal is, in decimal, each digit can be any digit between 0 and 9, whereas in binary, every bit can only be 0 or 1, which makes it a lot simpler. Now, in converting a binary number to decimal, if there is just one leading 1 followed by a number of trailing zeros, all you have to do is count the number of trailing zeros, and that number represents 2 to that number. So for example, here I have 3 trailing zeros, so this represents 2 to the 3 or 8. Here I have 5 trailing zeros, so this represents 2 to the 5 or 32. And here I have 10 trailing zeros, so this represents 2 to the 10 or 1024, or more colloquially 1024. If the number is not a power of 2, then we just have to determine the appropriate powers of 2 corresponding to each 1 bit and add them up. So, for example, here we have the number 1101. This represents 8 plus 4 plus 1. Why? Because we have 1 times 1 plus 0 times 2 plus 1 times 4 plus 1 times 8. This equals 13. Okay, here's another example. Here we have the number 101010. This represents the decimal number 32 plus 8 plus 2, because we have, starting with the least significant bit, the one on the right, we have 0 times 1 plus 1 times 2 plus 0 times 4 plus 1 times 8 plus 0 times 16 plus 1 times 32. And this equals 42. Here's our third example. This represents the decimal number as shown here, because we have 1 times 1 plus 1 times 2 plus 0 times 4 plus 1 times 8 plus 0 times 16 plus 0 times 32 plus 1 times 64 plus 1 times 128 plus 0 times 256 plus 0 times 512 plus 0 times 1024 plus 1 times 2048. Adding all of these up, we get the value 2,251. Now here are some exercises for you. I'd like you to pause the video and try these out. Now, I'm going to help you a little bit. Here are successively higher powers of 2. While the first few are quite straightforward and you've probably memorized them from the Inchworm song, some of the larger ones may be less familiar to you. So I'd like you to pause the video now and try converting these into decimal numbers. Alright, welcome back, and here are the solutions, and hopefully you got these. If not, try to figure out what the problem is. If you can't figure it out yourself, ask your friends or a teaching assistant. To convert a number that is in decimal to binary, this is a little bit more involved. What we're going to do is we're going to repeatedly divide the number by 2 but save the remainders. So to convert 13 to binary, we notice that 13 is equal to 2 times 6 plus a remainder of 1. Now 6 is 2 times 3 plus 0 because it's even. 3 is 2 times 1 plus 1. 1 is equal to 2 times 0 with a remainder of 1. All right, now that this value here is 0, we are complete. We will now read the digits from bottom to top. So we'll write down 1, 1, 0, 1, and we'll prefix it by 0b to indicate that this is a binary number. So 13 in binary is 1101. All right, let's convert 1970 to binary. 1970 is equal to 2 times 985 plus 0. 985 is equal to 2 times 492 plus 1. 492 is equal to twice 246 plus 0. 246 is twice 123 plus 0. 123 is twice 61 plus 1. 61 is twice 30 plus 1. 30 is twice 15 plus 0. 15 is equal to twice 7 plus 1. 7 is equal to twice 3 plus 1. 3 is equal to twice 1 plus 1. And 1 is equal to twice 0 plus 1. Once again, we finish as this value or number here is now 0, and we will read the digits from bottom to top to give us the numbers from left to right. So in binary, 1970 is, reading from the bottom, 1 1 1 1 0 1 1 0 0 1 0. And once again, we will add a 0b in front just to emphasize that this is a binary number. Once again, here are some exercises for you to convert a decimal number into binary. Again, I'd like you to pause the video and try to work these out. So, good luck. And welcome back. Here are the answers. Again, if you did not get these answers, try to figure out what you did wrong. And if you can't figure out what you did wrong, go ask a friend or to speak to a teaching assistant. Now, you may be wondering why we're always adding a 0b in front of every single binary number. Well, this is because this can actually be used in C++. Instead of having a literal integer, it is always possible to replace a literal decimal integer with its binary equivalent. So now when the compiler sees 0b 10101, it assumes that it can interpret the 1010 as a binary number and thus will assign n that value. In this case, that value happens to be 21, so if we execute this program, when n is printed out, it is still printed out in decimal, but its value is 21. Now, adding binary numbers. As with decimal addition, we just add the columns starting from right to left, starting at the least significant digit. But with binary, it's the least significant bit. We write down the ones unit of any sum and carry any remainder to the left if necessary. So for example, in adding these two binary numbers, we have 1 plus 1, 0 is 1. 1 plus 1 is 1, 0. We write down the 0, carry the 1. 1 plus 0 is 1. Next column, 1 plus 1 is 1, 0. We write down the 0, carry the 1. 1 plus 0 plus 1 is still 1, 0. So we write down the 0 and carry the 1. 1 plus 1 is 1, 0. So we write down the 0, carry the 1. 1 plus nothing else is 1. And so we've summed these two numbers. Here's another example. Starting with the least significant bit, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 1 is 1, 0, so we write down the 0, carry the 1, 1 plus 0 is 1, 1 plus 1 is 1, 0, we write down the 0, carry the 1, 1 plus 1 plus 0 is 1, 0, we write down the 0, carry the 1, 1 plus 1 is 1, 1, because it's 3. And so we write down the 1's unit, which is 1, and we carry the 1, and then we carry on to some 1 plus, well, nothing else, and that's that value there. All right. All right, here again are some exercises for you. Pause the video and try to calculate each of these sums of binary numbers. So, good luck. All right, welcome back. And here are the solutions. Once again, if you don't get these answers, ask a friend or go speak to a teaching assistant. You can, of course, always check your answers yourself using C++. Here I have a program where I have entered m and n as two binary numbers. I then calculated the sum myself and entered that sum as a binary number here. Now I will print both m plus m and indicate that that should be equal to my sum. So when I execute this program, fortunately I get 872 does indeed equal 872. All right, to convert a binary number to its hexadecimal or base 16 representation, we proceed as follows. Starting from the right, group the bits into groups of 4. Pad to the left with zeros as necessary in order to create a multiple of 4 bits. Next, replace each of the 4 bits with its corresponding hexadecimal digit as shown in the table on the right-hand side. We generally will give you such a table, but you can also very quickly write this table down. So here's an example. Here's a binary number, and we'd like to convert it into its hexadecimal representation. Easy enough. We will group the bits into 4s starting on the right. Now, notice on the left we have only 2 bits in the last group, so we will group that into create a group of 4 by adding 2 zeros to the left. Now we're going to proceed by converting each of the numbers each of the groups of 4 into its corresponding hexadecimal digit. So 0011, well, 11 is 3. 1100 is C. We already know that 1010 is 10, or A. Well, the next one is just 1. The next is 1001, which is 8 plus 1, or 9. The next one is 8. Now, the next one, 1110, comes right before 1111, which is F, so that must be E. 101 is 5. There's another 5. And the last one is 2. Thus, the hexadecimal number that represents this binary number is as shown here. Okay, let's try another one. Here is a 32-bit binary number. That is, there are 32 bits. The first step we take is group them into 4s, starting from the right. Now, 32 is already a multiple of 2, so we don't have to pad to the left. Once again, doing the conversion, the first one is 0. Next, we see a 110, or 6. 1011 is B. That's 7. 1101 is D. 1011 is B, 100 is 4, and 111 is F. And thus, the hexadecimal representation of this 32-bit number is this 8 hexadecimal digit number. All right, here again are some exercises for you. Pause the video and try to calculate each of these sums of binary numbers. So, good luck. All right, welcome back. And here are the solutions. Once again, if you don't get these answers, ask a friend or go speak to a teaching assistant. Now, you can actually test this yourself as well. So here I have a very small program where I entered two numbers, n sub bin and n sub hex. Now, the first one starts with 0b, so that indicates that the bits that follow represent an integer, but in binary. The next line has 0x. As you may have guessed, this means that the digits that follow are hexadecimal digits, and the compiler will then calculate what 2a is in hexadecimal as a hexadecimal number. It will then store that number. Now, when we print both of these out, the print command simply prints the decimal value of what is stored in those local variables. And so if those represent the same number, their values should indeed be the same, but they will be printed in decimal. So if I execute this program, I get the output that 42 equals 42. So yes, the hexadecimal representation of 10, 10, 10 is 2a. Next, to convert a hexadecimal number back to binary, it's reasonably straightforward. Replace every single hexadecimal digit with its corresponding 4 bits. This includes 0. So, here's a hexadecimal number. I'll replace the 5 with 0, 1, 0, 1. I'll replace the A with 1, 0, 1, 0. I'll replace the 3 with 0, 0, 1, 1. I'll replace the 9 with 1, 0, 0, 1. I'll replace the 2 with 0, 0, 1, 0. And I'll replace the 3 with 0, 0, 1, 1. All right, I can now take off the 2 leading bits and replace that with 0b, just to emphasize that this is a binary number. Okay, here's another example. Once again, starting on the right, F is 4 ones, E is 1110, D is 1101, C is 1100, B is 1011, A is 1010, and 1 is 0001. Once again, I can take off or strip the leading zeros, and I'll replace that once again with 0b, just to again emphasize this is a binary number. All right, here's some exercises for you. Convert the following 6 hexadecimal numbers back to binary. Now, pause the video now and try this for yourself. Welcome back, and here are the solutions. If you did not get these, try to determine what you did wrong, ask a friend, or go speak to a teaching assistant. Now, you can skip this slide if you want. However, here we are going to convert a decimal number into a hexadecimal number. And to do so, we simply divide the number repeatedly by 16 and save the remainders. So, to convert 6,543 into hexadecimal, we note that 6,543 is 16 times 408 plus 15. 408 is 16 times 25 plus 8. 25 is 16 times 1 plus 9. And 1 is 16 times 0 plus 1. Once again, we now stop because this digit, or this number here, is now 0. We now read the digits off starting at the bottom. So 1, 9, 8, 15. Oh wait, 15 is the hexadecimal digit F. All right. Now we prefix it with 0x, and so the hexadecimal representation of 6,543 is 198F. Now, to convert a hexadecimal number back to decimal, we do the same thing we did with binary numbers, but we use powers of 16. So, to convert the hexadecimal number 3B0F5 to decimal, we just write it out as 3 times 16 to the 4 plus b times 16 to the 3 plus 0 times 16 squared plus f times 16 plus 5 times 1. Now, but b and f are not decimal numbers. However, that's not a problem because we're just going to replace b with 11 and f with 15. So now 3 times 16 to the 4 is that number there. 11 times 16 cubed is about 45,000. 0 times 16 squared is just 0. 15 times 16 to the 1 is just 240. And 5 times 16 to the 0 is just 5. Adding those up gives 241,909. Reasonably straightforward enough. It's the exact same operations we did before. Alright, now, to learn to multiply two binary numbers, first recall from elementary school how you multiplied two decimal numbers. So suppose we're multiplying these two decimal numbers, and we put the smaller one second just to minimize our work. First, we multiplied the least significant digit of the second number by the first number. So 6 times 4,533 is 27,198. Then we multiplied the first number by the second digit, and we added a 0. This is because we're actually multiplying 4,533 not by 5 but by 50. Then we multiplied 4,533 by 2, but we added 2 zeros. Why? Again, because we're actually multiplying 4,533 by 200. That gives us 906,600. We then added these three numbers together to get the product. Well, oddly enough, we do exactly the same thing when multiplying binary numbers. Only it's much easier now because the only thing we can multiply by is 0 or 1. So here are two binary numbers we'd like to multiply. Well, 1 times the first binary number is that binary number. 0 times the first binary number is just 0, but we're just going to draw that one extra 0 there to emphasize that. Next, multiplying the third bit from the right of the second number, we have 1 times the first number is that, and we pad with 2 zeros. Next, 1 times the first number is the same number, and we pad with 3 zeros. The next digit is 0 again, and the most significant digit of the second number is 1, and so therefore we multiply 1 by the first number. And now all we do is we add these up. So in the first column we just get 1, in the second column we get 0, in the third column we get 0 and we carry a 1, so on and so forth until we get our solution. And so the product of the first number times the second number is the number we see here.